Hello, good afternoon. My name is James Nyako, and I'm I'm presenting in the name of Group 12, and my topic is types and characteristics of machine instructions. So let's get started. So before that, you have to know the meaning of machine instructions, and as we have over here, machine instructions are low-level commands that a computer's processor can understand and execute. So in this way, the computer have to understand it before it can actually follow or perform the instructions you want it to. And um, the next slide also makes us understand or makes us know the characteristics of machine instructions. And over here we have they are written in low level language as explained earlier on in the definition. Then the second one also makes us understand that machine instructions are composed of binary codes, typically represented as series of ones and zeros. So, like the way we've been doing in the Boolean algebra, sorry, Boolean expression and all those stuff here, zeros and ones, they are executed sequentially by a computer's processor. Each instruction performs a specific operation such as the arithmetic calculations, data movement, or control flow. And the fifth one also makes us understand that they can manipulate data stored in the memory or registers. And the sixth one is they are encoded with specific opcodes that determine the operation to be performed. The seventh one also explain to us further that they can be they include operands that specify the data to be operated on. And the eighth one is they can modify a program counter to control the flow of execution. So it actually controls a counter so that execution won't be like hazardous or it will come in order. And they can interact with input and output devices like using the keyboard and mouse to, you know, typing something on the keyboard actually it's an instruction. So when you are using when you are actually talking about machine instruction, keyboard and mouse are supposed to be part because they also send commands to the computer to be executed. And the tenth one is the fundamental building block of computer programs. They are the fundamental building blocks of computer programs. So it means that before a computer is supposed to, perform its tasks, instructions are supposed to be fundamentals of it. So moving on to the next slides, we have the types of machine instructions and the machine instructions. So types of machine instructions, we have the arithmetic instructions, that's the addition, subtraction, multiplication, and division of the instructions. We have logical instructions, which is the Boolean expression, the AND gate, the OR gate, the NOT gate. Yeah. And we have data transfer instructions, we have control instructions, we have input and output instructions, read and write. So in this case, the write can be you typing, and the read will be what you are typing shown as a software displayed on your monitor screen or your laptop screen. And we have the compare instructions, we have the shift instructions, we have the stack instructions, we have the floating point instructions, we have the system instructions, we have the conditional instructions, and the last but not the least, we have the rate manipulation instructions. This is all for my presentation.
Uh, Hello, my name is Buffy Ford, and I'm doing a joint present from Group 12, and I'm doing a joint presentation on instruction addressing mode with nothing. So basically, instruction addressing modes are aspects of the aspects of the instruction set architecture, most central processing unit designs. They are way in which the operands of an instruction is specified. There are addressing modes that's defined in the given structure set architecture define how the machine language in that architecture opens of each instruction. These are addressing modes specifies how to calculate the effective memory addressing of an operand by using information held in register and or constant contained within a machine instruction or somewhere else. The addressing modes specifies a rule for interpreting or modifying the address field of the instruction before the operand actually executes. So basically, this talks about the definition and the uses of the of instruction addressing rules. So generally, different artists and computer manufacturers give different names to the same addressing modes or same names to different addressing modes. Since there are no general accepted names for addressing modes. Furthermore, an addressing mode which in one given architecture is treated as a single addressing mode may represent functionality that in other architecture is covered by two or more addressing modes. So examples are some architecture sets computer some example is a complex instruction set computer architectures such as digital equipment operations, but they treat registers and literal or mediate constants as just another addressing mode. So, some instruction set architectures such as Intel x86 and IBM 360 and its processors have a low defective addressing instructions. This calculates the effective operand address and loads it into a register without accessing the memory it refers to. This can be useful when passing the address of an array element to subroutine subroutine. It may also be a clever way of doing more calculation than normal in more instruction. For example, using such an or a instruction with the address mode base plus index plus offsets. It allows one to add two registers and a constant together in one instruction and store the results in a third register. Um, Computer architectures vary greatly as the number of addressing modes they provide in hardware. There are some benefits of eliminating complex addressing modes and using only one or few simpler addressing modes. Even even though it requires a few extra instructions and perhaps an extra register, it has proven much easier to design pipeline CPUs if the only addressing mode available are simple ones. Um, so we have types of instruction addressing modes, and we have uh, we have immediate immediate mode, direct mode, indirect modes, index mode, relative modes, and each of the modes listed has its own way of specifying the memory location or data needed for an instruction to be executed. So from Nati, Aaron will come and explain the rest, uh, the types of the instruction instruction addressing modes.
Okay, I'm Aaron and I'm here to continue where the board has ended. And I'm here to talk about instruction address, types of instruction address modes. and there are about five. So come to one, we have the immediate mode, direct mode, very indirect mode, index mode, and relative mode. And each of these modes listed has its own way of specifying memory location or data needed for an instruction to be executed. And with immediate mode, which was the first one I mentioned earlier, immediate mode, the operand or the data is directly specified within the instruction. Immediate mode allows values to be used as operands without necessarily accessing the memory. And with the direct mode is an addressing mode where the operand or data is accessed directly from a specific memory location. Direct mode allows instruction to directly reference a memory address to and with indirect mode, the operand or data is accessed indirectly through a memory address stored in register or memory location. So by allowing instructions to directly determine the memory location to access, it provides what? Flexibility. And then index mode, instructions are allowed to access data by adding an offset or index value to a base memory address. It helps in accessing elements in arrays or data structures where the index specifies the position of the required data. Relative mode. With relative mode, it is an addressing mode where the operand is accessed relative to the current program counter or instruction. Relative modes, they are allowed to refer to data that is near the current word function, which makes it useful for jumping or branching to different parts of the program.
Hello everyone, I'm in the person of Nigel AJ, and I'm here to discuss the topic scalar processing. Scalar processing refers to the execution of operations on individual data elements one at a time, rather than performing operations on multiple data elements simultaneously. In scalar processing, each instruction operates on a single data item, performing arithmetic, logic, or other operations. The data can be integers, floating point numbers, characters, or other basic data types. This traditional method of processing data is straightforward and easy to understand. It forms the backbone of most early computer systems and is still prevalent in many aspects of modern computing. This means that data element is processed individually and step by step. That's what this scalar processing is basically talking about. Scalar processors. Scalar processors are a type of CPU, central processing unit, in computer architecture that primarily handle individual data elements one at a time. They process single data items such as integers or floating point numbers using a sequence of instructions. This is in contrast to vector processors, which can perform the same operations on multiple data elements simultaneously. This is also basically talking about the CPU that carries out the operations on each data element sequentially and one after the other. Characteristics of scalar processors. Single data stream. Scalar processors execute one instruction at a time on a single data item. Each instruction operates on a single value, performing arithmetic, logical, or other operations. Sequential execution. Instructions are processed in a sequential manner, meaning each instruction must complete before the next one can start. This limits the potential for parallelism within a single instruction stream. Simplicity. Scalar processors are relatively simple to design and understand, which makes them well suited for tasks that don't require extensive parallel processing, such as basic arithmetic calculations and simple logic operations. Programming ease. Writing software for scalar processors is straightforward since programmers don't need to consider complex parallelism. This makes scalar processors suitable for beginners and for tasks that don't involve heavy computational demands. Advantages of scalar processing. It's simple to implement, making it a good choice for tasks that don't require massive parallelism or complex mathematical operations. It's also more intuitive. It's also more intuitive to program for beginners and works well when dealing with irregular or conditional tasks. Scalar processors are often highly optimized for common operations, leading to efficient execution of many everyday tasks. Disadvantages of scalar processing. It can be chained because it uses 64 bytes each clock. It makes memory delay visible. The price is high. That's for number 3. Yeah. Fetch one instruction and decode it. Dispatch for each job. That's for number 4. Limitations in scalar processing. Number 1, limited parallelism. Scalar processors are less efficient for tasks that require processing large amounts of data simultaneously. They can't exploit parallelism inherent in certain algorithms or datasets. Number 2, performance bottlenecks. In applications involving complex simulations, data analytics, and other intensive tasks, scalar processors can become performance bottlenecks due to their inability to process data in parallel. Number 3, inefficient for vector operations. Algorithms that involve repetitive operations on arrays or large datasets might require numerous individual scalar operations, leading to slower performance compared to vector processors. In conclusion, scalar processing forms the foundation of computer architecture and its approach. We, oh, in conclusion, scalar processing forms the foundation of computer architecture and its approach we started with in the world of computing. While it may have limitations in terms of handling massive datasets and parallelism, it's widely used for various applications due to simplicity, efficiency for certain tasks, and ease of programming. Thank you.
Well, sure, Jessina, I really wish that, and presenting on performance instruction pipelining. What is performance instruction pipelining? Imagine building a sandwich. Each worker has a specific task like spreading the mayonnaise or adding lettuce. Similarly, in a computer, instruction pipelining breaks down tasks in a program into smaller steps. These steps are performed one after the other by different parts of the processor. This helps a computer complete multiple instructions at once, increasing efficiency and speed. There are 5 stages in the performance instruction pipeline. The first is the fetch stage. The fetch in the fetch stage, instruction is being fetched from the memory. The second is the decoding stage, where the instruction is decoded to determine its type and the operations it requires. The third is the execute stage, where computations or calculations are performed. The fourth stage is the memory stage. If the instruction involves memory access, such as loading memory access or storing data, it is done here. And the fifth stage is the write back stage. The final stage writes the results of the instruction back to the register file. In performance instruction pipelining, hazards can occur and impact the efficiency of the pipeline. Hazards can be broadly classified into 3 types. We have the structural hazards, data hazards, and control hazards. With the data hazards, it occurs when an instruction depends on a previous instruction that has not yet been computed. There are 3 types of hazards, which you can see on the screen. Techniques like forwarding can be used to resolve data hazards by forwarding the required data directly from the previous instruction to the dependent instruction. Then we have the structural hazards, which occur when multiple instructions require the same hardware resource at the same time. Techniques like resource duplication or scheduling can help mitigate structural hazards. We have the control hazards. Branch instructions can create control hazards as the pipeline may have already fetched and partially executed subsequent instructions. Techniques like branch prediction help mitigate these hazards. So we have the CPI or clocks or cycles per instruction. This measures the average number of clock cycles required to execute one instruction. A lower CPI indicates better performance. Pipelining aims to reduce the CPI by overlapping the execution of multiple instructions. Speed up measures the improvements in performance achieved by using pipeline compared to a non-pipeline processor. It is calculated as the ratio of the execution time for a non-pipeline processor to the execution time for a pipeline processor. A higher speedup indicates better performance. Thank you.